This is the audio notes for bond energy calculations in Chem 1. Before we get into the calculations that we're going to be doing, we need to remember what a covalent bond is. Covalent bond is a sharing of electrons. Um, Electron orbitals overlap and are attracted to both nuclei. So for example, in the picture on the upper right hand corner, here is a single hydrogen. Again, Lewis dot has it having one electron. Positive nucleus, one electron on the outside. A diatomic hydrogen, each hydrogen would have electrons, so sometimes the Lewis dot for a hydrogen molecule is represented with the two electrons in between, but often we would draw that line. And what that line represents is an overlapping. It's almost like a Venn diagram where in between the two is the two electrons. These are attracted to both nuclei. This creates a bond. Bond energy is referring to the energy required to break that chemical bond. So since there's attraction between positive and negative, there must be energy needed to overcome that attraction. And this is a calculation that we can do within chemical reactions. So the first thing to point out is it requires energy to break a bond. Atoms are more stable when they are bonded because they're at that octet, that stable outer shell configuration. To make something go from stable to unstable, it requires energy to undo. Second bullet point to be aware of. Shorter bonds, so if the bond length is shorter between two atoms, will require more energy to break that bond. If you think about it, a shorter bond means the electrons are closer to the nuclei. They're more attracted. To break up more attraction takes more energy. Single bonds, by the way, are longer than double bonds. If you don't remember double bonds, that's when we drew two lines in between two atoms. We'll show you that in a little bit. And double bonds are longer than triple bonds. So hopefully you can deduce from this that a triple bond would require more energy to break apart than a double bond. A double bond would require more energy to break apart than a single bond. On the other hand, if breaking bonds takes energy because you're overcoming attraction, you're undoing stability, forming bonds will give off energy. Because when atoms become more stable, energy is released. So what we're going to be doing is we're going to be looking at that balance in a chemical reaction between gaining energy to break bonds and giving off energy when new bonds are formed. On these pages in the book, there are tables that show here's the bond, here's how much energy it takes to break that bond. The unit for bond energy is a kilojoules per mole. So remember, joule is the unit of energy. Kilo is just a metric prefix because it's a fair amount. And per mole, because if we did this per atom, it would be a tiny number. So we need enough of something to actually make this calculation have reasonable values. What we're going to do is a practice problem. This is a practice problem with a reaction that we have looked at in a lab activity recently. It says how much energy is needed or created during the decomposition of hydrogen peroxide. If you are given a bond energy problem, either you will be given a list of here are the different bonds and how much energy is associated with them, or you'll be given a big data table like on page 172 or 177. In this particular problem, you are just given here are the different bonds, which is kind of a helpful hint for you because you're going to need to know how to draw the Lewis dot for things. However, I'm getting ahead of myself a little bit here. Similar to stoichiometry, if you're given a problem like this, the first step is to balance the chemical equation. Second step is to draw the Lewis dot for each atom, because you need to figure out the total number of bonds for each thing. And then is our equation. This is the summation symbol, the bond energy of the reactants minus the sum of the bond energy of the products. Another way that this is often looked at is input minus output. As we had to put in energy to break apart reactant bonds, minus energy given off, output, when new, more stable bonds are formed. Recall when I talked about how to write balanced equations, a chemical reaction is kind of like a jumble where you break things apart, you mix them around, and you form new things. Well, we got to break things apart, that's the reactants. We need to form new things, that's the products. Last thing to mention on this slide, when you do this math, which again I will show you in a minute, at the end of the problem, if you get a negative answer, a negative value means more was given off, output, than was put in, input. Think about that. A small value minus a big value would give you a negative number. So that would refer to as an exothermic reaction. Negative values in thermal chemistry refer to the system giving off energy to the surroundings. On the other hand, if you did this equation up here, reactants minus products, and it gave you a positive value, that would be endothermic. More energy is put in to break the reactants than is given off when new products are formed. So what I'm going to do is I'm going to start with part one. So I gave you the steps of how to solve this. Let's start with part one. Write the balanced equation. So hydrogen peroxide is H2O2. If it's a decomposition reaction, it is the only reactant. Maybe some of you remember when we did this with the little film canisters the other day, and we did our flame test with the splint, O2 gas was given off, and water is our other product. In order to do bond energy, much like in order to do stoichiometry, we need a balanced equation. You notice that the hydrogens are balanced, however the oxygens are not. And the way that I can balance the oxygens is by putting a 2 in front of the water to give me 4 oxygens on the right-hand side, and a 2 in front of the hydrogen peroxide to give me 4 of each hydrogen and oxygen now on both sides. So again, step number one is writing out the balanced equation. Step number 2 is drawing the Lewis dot for each atom. Oxygen, for example, has 6 valence electrons. If you have a second oxygen, they will create a double bond. So in other words, the Lewis dot for oxygen is O double bonded to O. When we are counting our types of bonds, this is 1 double bond. Some students get confused and call this 2 single bonds, but it's a different value for the 1 double bond. Lewis dot for water, hopefully we know this. I've had you draw this in several units. We don't need the partial positive and partial negative ends, but what you can tell is that there's 2 HO bonds. Lastly, we get to hydrogen peroxide. Hydrogen peroxide is the only Lewis dot that you might not be as familiar with. But if I start with oxygen, I would single bond the 2 oxygens together and then realize that I have a bond to hydrogen and another bond to hydrogen that I can make. So I have 2 different types of bonds in this particular one. I have the 1OO bond and I have the 2 OH bonds. So what's important to note here is I need to figure out my total number of bonds. Now if we go to solving for bond energy, it's going to be reactants minus products. So the bond energy of reactants minus the bond energy of the products. Let's go back up to our equation for a second. There's two hydrogen peroxides on the reactant side. Within the hydrogen peroxide, there are two different types of bonds. There's HO bonds and OO bonds. So my bond energy will equal, I have HO bonds, and I have OO bonds. In one hydrogen peroxide, my picture shows that there is two, again, 1, 2 HO bonds. However, if you look at the top of the screen, there is two hydrogen peroxides overall. So if one hydrogen peroxide has two HO bonds, two hydrogen peroxides would have 4 HO bonds. Similar thing can be done here. So since we have two hydrogen peroxides and each hydrogen peroxide has one OO bond, I'm also going to put a 2 coefficient in front of here. This is all of my reactant bonds. If I subtract my product bonds, notice that there is one OO double bond in diatomic oxygen, and there's a coefficient of 1 in front of the oxygen in the balanced equation. So I have one OO bond. As for my water, there are two HO bonds in one water, but there are two waters in the balanced equation. So that means I have a total of 4 HO bonds. At this point, what you are now able to do is to plug in those values. Remember on the previous slide, I gave you values for these things. So for example, 4 times what an HO bond is, an HO bond is 459 kilojoules per mole, plus 2 times an OO bond, which is 142. Save space, I'm not going to write the units right now. If I add all that up, I can then subtract the OO double bond, which is 499, plus the 4 times the HO bond on the other end, which is 459. If I do all of this math, I end up getting negative 215 kilojoules per mole, which means that heat is given off in this reaction. It is an exothermic process. Perhaps some of you on that day when we were dealing with the film canisters grabbed the film canisters and felt that they were getting a little bit warm because the reaction was giving off heat. That heat was then being absorbed by the film canister itself. That's why it felt warm. If I go back to my PowerPoint here, once again, the steps that we took was we balanced the equation. We figured out the total number of bonds. Remember, reactant bonds have to be broken. Product bonds get formed. And then we did our math. Reactants minus products, making this an exothermic reaction. This is a term that you do need to be aware of. So what we're going to be doing is having students then practice bond energy problems. Combustion reactions are very common that we will use to practice bond energy problems with, but as you saw with this decomposition example, they're not the only types of problems that we'll have students do. Remember your steps. You have to write a balanced equation. You have to draw the Lewis dot. And then lastly, you have math to perform in order to get to your final answer. This concludes the notes on bond energy.